see if this is working. Yes, hi everyone. I'm Ragnhild Skagestad working in SINTEF, and I'm very glad to be here. This is my first CO2net GeoNet Forum conference, and I really enjoyed it. And I was a bit scared that I wouldn't understand anything of all this geological part, but there have been really nice discussion and learned a lot. So thank you for the earlier speakers. So I'll just start saying a few words about SINTEF. This is one of Europe's largest independent research organization. We are more than 2,200 employees, and I'm not sure how they have counted, but someone had counted 6,400 projects per year. At least we have a lot of projects. Focusing on of course, SINTEF is focusing on a lot of different areas. My group and my team has over 20 years experience and focusing on the CCS chain. It starts with techno-economic assessments and feasibility studies for the CCS chain. I can just say as a curiosity, when I started working with CCS for 20 years ago, one of our first studies was a feasibility study for a cement plant in Brevik in Norway. And now, 20 years after, last year, they actually started to capture the CO2. So I have been on a long journey, waiting and waiting for things to happen, and now it is. Our focus is optimizing logistics from source to sink. So we are not that into capture, not into storage, but all things between that. We have a quite heavily focus on ship transport. I'll come back to that, and thereby also the intermediate storage and cost estimation for early phases and scale up. We have in SINTEF, there's a lot of great ideas that works very well in lab and in low TRL, and our task is to how will this look in a big scale. So we are used to talk about big scale, large money, large volumes, and do a lot of EU projects, CTPs, JIPs, and stuff. So for the CCUS value chain, what's the problem there? The potential for CCS in Europe and in the world are high. There are so many projects, so many startups and things that are going on now, but still very few projects make it through the final investment decision. We see that things step up, things getting delayed, there are new things popping up. So why is that happening? We see the technology there, we have it's possible to capture, it's possible to transport, and definitely possible to store, but the main issue is cost and timeline and the risk. And not the risk for leakage or such a thing, but risk for the emitters to not be able to be sure that the CO2 is stored, and also for the storage part to be sure that they have CO2 to store. So how to build these chains together, and how to use those, both the cost, time for the project, and risk for accelerating the CCS. So the main point is to go from this. We have a emitter, we capture it, have the pipeline, and into a reservoir. Quite easy CCS chain. But it's not how it looked like when we start project. We are building these kind of networks with several emitters and several transport modes. We have intermediate storage, we have reservoirs. And of course, adding all this into a CCS chain means it adds complexity, but it also adds flexibility. If one of these sources somehow stop producing or have any problems, the rest of them will produce CO2, and then we'll be able to store it. On the other hand, if there are issues with some of the intermediate storage or the transport modes, there are possibilities to get around it. So having several players in the chain gives complexity, but it's also a value on that. I will focus a bit on these different parts of the chain, starting with the emitters. And the emitters are normally like industrial sources, waste. Now there's been a lot of focus on waste to energy plants because they have this bio and CO2, so they can, if they store that, if they have a possibility to earn some money. And it's rather small. Of course, there are larger sources as well, but when we see what kind of volume they are intended to capture, it is more or less between 0.5 to 1 million ton. And it's quite scattered or clustered, but it's on land. It's there because they have raw material there, they have energy there, they have people who work there, and there's always been there. So that's why they're there. And they have normally very limited area space available. And their main focus is not CCS. Disappointingly, it's not. They have their main core business. They produce steel, they produce cement, they produce whatever they earn money on their purpose. But they have to do CCS to reduce their emission or to make their product more green. So CCS is often, not always, but often, one of several options for reducing this emission. They could go for fuel shift, they could go for electrification, they could for improve the process, other things. And CCS requires energy, cooling water, where they need to treat maybe waste according to the capture, and it's quite costly. So we have to show that CCS is a viable and safe and method to reduce their emission. And of course, if they are investing up to 1 billion euro, they have to be sure that this CO2 is removed and stored and taken care of. Going to the storage side, the CO2 storage, that's the core business of the storage. That, of course, it's dependent on geology. You cannot make a storage whatever you want. You have to test and find, and up to now, it's not been that many licenses for CO2 storage, but we have learned these couple of days that there's a lot of things going on, and there's a lot of potential. So it is also require often larger volumes. It's 3 to 5 million ton over 20 years, for instance, and also these long contracts. If you are putting so much money as it costs to develop a storage, CO2 storage, then you definitely have to be sure that there are CO2 available, and you will get paid for this effort. Going to the logistic part, I've just put on ship and pipeline and road and rail. CO2 pipelines is quite common. We have a lot of experience with CO2 pipelines in the US, and also now a few pipelines in Europe. Also we have offshore pipeline in Europe that are in operation now. We have what is the main characteristic with pipelines. They have high capex. It's quite costly to build. It's having high pressure CO2, large volumes, and the cost when you have built a pipeline from A to B, it's there from A to B, and the size is the size you have chosen. So, like Owen was saying, it's a bit difficult to say how large should that pipeline be to also be able to increase your project for next phase, or new emitters coming in. So we also, if we look at the ship transport is quite flexible. Of course, it requires K, and it's intermediate storage, and it's not just a ship when you have that into a CCS chain, but it is very flexible. It gives batch-wise CO2, so it gives CO2 now and then, and we have transported it in liquid phase, which is normally low temperature, low pressure compared to pipeline. Today there are 6 ships in operation, and we know that the Northern Lights has several ships in the pipes, so that's very good. And we have also a lot of experience with ship transport of food-grade CO2. So we know about handling CO2 by ship, and of course the shipping industry is tremendously, so we know how to transport gas. For road and rail, it's most likely that that will be for small volumes. We have the infrastructure already built, but it also need intermediate storage, and it's more or less for smaller volumes. There will be, for the Celsio case in the Northern Lights project, they will have part of their transport chain with road transport. So, and they are capturing 350,000 ton per year. So it's definitely, it's not that small scale, but still that requires a lot of lorries when these when we are using road transport. For all of these logistic part, it is a question about what size are we going to, what kind of pressure and temperature are we focusing on, what kind of materials are we needing, and can we build, for instance, ship, can we use it for other purposes as well. I will go a bit more into the ship transport part. As I said, we have 6 ships in operation today, and they are like 1,500 to 7,500 cubic meters. So they are not a very large ship. We know the Northern Lights have ordered 3 more, which is up to 12,000 cubic meter, and there's a lot of design and a lot of plans of CO2 ship that are much bigger, up to like 50,000 cubic meter. There are some issues with that. I'll come back to that. What is very good with ship transport, it's very flexible, both over time. You can use the CO2 ship for a couple of years, and if the volumes or if anything changes, then you can use it in another project. And you can also, if there's something happening to the chain, you can maybe direct the CO2 to another storage area. So, and it's very cost effective for a bit smaller volumes and longer distances compared to pipeline. You can also build these multi-gas carriers where we can, then it's built for several types of cargoes with several different gases, but of course you have to be sure that the material and the pressure is okay. We also see that ship transport reduces the risk and add flexibility, as I said, but the question and discussion around this now is around impurities and pressure and temperature. For this larger scale, as I was talking about, 50,000 ton, you would go down to low pressure to be able to gain more CO2 in the ship, and then you will have if you have lower pressure, it means lower temperature. So that is a challenge. What is good with the ship transport solution is it can have offshore unloading. That gives us new opportunities. We don't necessarily need intermediate storage. We can have CO2 be delivered at the reservoir or to a platform or a ship lying there for this maybe reduce some of the cost there. With the logistic part, we need also hubs and terminals. That, of course, the hubs and terminals connect sources to the sink. It is including intermediate storage and conditioning, purification and case. So it is quite a large process system. And it reduces the duplication and lower barriers maybe for new emitters to join the chain. But there are some issue and concern with the mixing, and I will come back to that. Just very fast on, we have together, SINTEF together with Brevik and this consortium in the CO2 loss project, we have developed a cost estimation tool where we can estimate CAPEX, OPEX, and also the emissions for CO2 transport. For all this, we can see what if we transport that amount at that pressure from location A to location B and then further to location C, what will that cost? So having this tool is a very good opportunity to investigate a lot of scenarios, and that is important to find the lowest cost on these logistics. I also like to highlight this Giga CCS project, which is a research center in Norway with 40 partners. And one of the, I'm not sure, there are 4 areas here: capture and CDR, infrastructure, storage, and then one on CCS value chain. So that is the one I'm working on, and our concern now is on this intermediate storage, where we look at mixing several CO2 sources, and we see that there are some issues with that. We are not completely sure how it will influence the material needed and purification needed to gain into the quite strict specification that we have. I will not go into that here, I'll run out of time, but we see that these specification, the purification needed to reduce the impurities in the CO2, and when we do the mixing in this hub, that's a challenge. So that's something we are working on now, and also on this hub design for making the best possible mixing places. So the key takeaways here is that CCS is technically feasible. It does take time to develop the storage and transport and capture at the same time, so building these chains are difficult, but it's definitely possible, and we see also that all CCS chains are one of a kind. We should be treated that way. We should look into all the different possibilities and see what can be done instead of digging into a lot of the problems. And we also see that the future here is to connect these emitters, infrastructure and storage to make scalable and flexible networks. And then I say thank you for your attention.